So we're looking here at the features of the graph. F of x equals, these symbols are what we call an absolute value bar. So you guys might need to write that down if you don't remember, because this is not the first time you've seen them. Absolute value bars. You should have learned about those right after you learn about negative numbers. So you first learn about negative numbers in, anybody remember what grade? Sixth grade is when you first talk about negative numbers on a number line. So absolute value comes shortly thereafter. So this is somewhere between 6th and 8th grade. You should have been doing absolute value of something. So let me just refresh your memory. What is the absolute value of negative 3? So do you have to write this down? The absolute value of negative 3 is 3. What's the absolute value of negative 15?
15.
It's 15. What's the absolute value of 7? It's 7. What's the absolute value of 0? 0. Okay, when you first learned about absolute values, the way they showed you is they said, think about a number line. If I want to know the absolute value of negative 3, what I want to know is how far away is the number from 0. So negative 3 is 1, 2, 3 units away. So the absolute value of negative 3 is 3. The absolute value of 7, well, that is 7 units away. And what do most people take away after they've seen absolute value? All they say is, oh, like what are y'all thinking right now? Oh, it's not the opposite. It's right. That's what people think to start with. But that's why I did the absolute value of 7. So maybe you wouldn't think it was opposite anymore. Right? Because the absolute value of 7 is itself. But the absolute value of negative 3 and negative 15 was positive 3 and positive 15. When we take the absolute value of a number, the result cannot be negative. Cannot be negative.
Is it just like consonant times 1?
Kind of. So this is good you are talking about this kind of stuff, because that's kind of what we're going to be focused on today with the graph of it. If I'm taking the absolute value of something that is negative, I want to multiply it by negative 1. Like the absolute value of negative 15, we'll multiply negative 15 by negative 1. If I'm taking the absolute value of something that's positive, though, I just want to multiply it by positive 1. Okay, so is there any confusion about what an absolute value function is? Everybody knows what these bars do. Okay. Now let's think about absolute value bars in terms of a function. So, quick review. What is a function?
Any definition?
This is why when y'all go next year and y'all start saying, I never learned this. Oh, baloney. You know how many days I ask you what a function is?
Every input has exactly one output. That's
Yes.
your definition.
A function is a special kind of relation. What's a relation? A collection of ordered pairs. Inputs, outputs, x's and y's. So here we go again. A function is a special relation where every input, x, has exactly one output, y. So here, if this is a function, because I'm in function notation, we can think about some of those inputs and finding out what their output should be. So what are some x values we like to plug in that are very easy to graph?
1, 2, 3, 4.
Okay, we do like 1 and 2. 3 and 4 are pretty easy as well.
Oh, you like 0.
We also like 0.
-1, -2.
These are normally the points we like to plug in. -2, -1, 0, 1, and 2. So let's think about these on a graph. You might have to give me just a second. It's been a while since I've used the graph. Okay, so I've got this coordinate plane. pulled up here? Can you guys see the grid?
I can't. It's just two lines.
Is it? So it's not just.
Why? Look at this.
Man, I can't see nothing like that.
Okay, hold on.
Why don't you
So we said if we think about it on a graph paper, these are the values we like to plug in. -2, -1, 0, 1, and 2. So let's figure out what would happen if we plug these values in to the function x. So if I plugged in a -2 for x, what would I be finding? I would be finding the absolute value of -2. Well, what is the absolute value of -2? 2. So that means the ordered pair -2, 2 would be part of my function.
You're great.
So here, if I go to -2, 2, I'm going left 2, up 2, plot a point. Next, let's look if the x value was -1. What if I plugged in -1 for x? What's the absolute value of -1? 1. Which means the ordered pair -1, 1 would be on my graph. What if I plug in 0? What's the absolute value of 0? Which means 0, 0 would be on my graph. What if I plugged in a 1? What's the absolute value of 1? Which means 1, 1 would be on my graph. What if I plugged in a 2? What's the absolute value of 2? Now, are these the only points that are on the graph? No. Remember, we picked these x's. We could pick any kind of x's we wanted to. What if I picked 3 or 4? What if I picked a half or a quarter or -1.5? Right? So all those points, remember how we had to connect them with a line to show all the answers. When you look at this, the dots I have, what shape does it look like it's going to be? Yeah. Remember when we did a quadratic function, an x squared function, and I told you it's a u, and you better draw a u, don't draw a v, because there is a function that is a v. Well, guess what the function that is a v is? It's the absolute value function. If I connect all of these points, this is what the absolute value function looks like. So it looks like a V. How else could you explain this?
Does it have like exponential growth?
Right? It's not growing exponentially.
It's just steady.
It's growing what? So if it's not exponential, what word do we use? If it has steady, constant growth.
Consistent growth?
It is consistent, but that's not the word we use.
No, you said it before.
Maybe. If you look at the graph, what kind of graph does it look like?
V.
It does look like a V, the shape of a V, but what else that we have graphed does this remind you of?
A parabola? Something like that?
It kind of looks like a parabola, but you said the difference is this one doesn't grow like a parabola does.
I could.
We have no idea.
What does it start with?
An L.
Linear.
There it is.
If it's not exponential growth, it's linear growth. Does this look like a line?
Yeah.
Kinda, but it also kind of looks like two different lines that
Connect.
met with each other. And then we started a new line. Does everybody see that? Two lines together? That's what we're focused on. We're going to be graphing functions that actually are different pieces of other graphs together. So in this case, a absolute value function is almost like graphing two lines and putting those two lines together for where they meet. This is called an absolute value function. All functions where you piece them together, those are called piecewise functions. That's what our whole chapter's on. from now to the end of school. Piecewise functions. Because they're in different pieces. Like here, it's 2 lines.
So on this, will you still have the x and y intercept where like
You can?
on
So let's-
the y intercept is 0 or whatever, and the x intercept would be 0 as well?
Yep. For this one, the x-intercept is 0 and the y-intercept is 0. What other features of graphs does this have? So we talked about an x and y intercept. What's some other things we looked at with graphs?
A vertex.
A vertex. Does this have a vertex?
Yeah, 0, 0.
It does. A vertex is just its highest or its lowest point. So its vertex is the origin. Okay? Anything else that this has?
Arrows that go.
It has arrows because these lines continue forever in one direction each.
Yeah.
Right? Okay? What about, what do we call this? You see what I'm drawing? That is the y-axis, that is the y-intercept, but in this case, it is an axis of symmetry.
So you minus the greatest and the least. So you put them on.
So in this case, the axis of symmetry, sorry, you can't see that in green, can you?
Kind of. A little bit.
Here, that would be at x equals 0. Remember, the axis of symmetry is always x equals a number. All right, let's talk about some more things we talk about with graphs. We also spend a lot of time talking about domain and range with a graph.
All x and all y.
So the domain is the list of all possible x's. So what x's could we plug in? And look at the graph. What all x's does this cover? All of them. It covers every x possible.
From negative infinity to infinity.
So the domain
Covers every y as well, doesn't
is from negative infinity to positive infinity. That's my domain. It goes all the way left to all the way right. Negative infinity to positive infinity. That's the list of x's. What about the range?
All list of possible y's.
All the possible y values. So what's the lowest y value it goes to?
Negative infinity.
Does the graph go down here?
Is
0.
0. So the lowest y value is 0. Up to a highest y value of
Infinity.
infinity. So the range is always in one direction. Think about how it worked with the quadratic functions, right? The u's. They didn't go from negative infinity to positive infinity either, because they have a vertex. If there is a vertex that is the highest or lowest point, it can't go from negative infinity to positive infinity on the range. Yeah, so what we're doing now is we're graphing an absolute value function on the board. I'm going to try to record it here where you guys can see it. Hopefully you can see what's going on. At this point, hold on. There it goes. So we are recording absolute value function. I don't need to do that. Stop recording. Give me just 1 second. Delete. Okay, so here is how you get the absolute value put up there. So we clicked y equals. Make sure everything's cleared out. So is everybody here? Y equals, everything's cleared out. Let's click zoom. Let's click 6. That way all of our graphs look the same. It should look like this. Is everybody's working like this? Anybody's not working?
Mine has a little thing on the. I'll have to come show you. I don't know what it is.
Yeah, that's fine.
A little thing.
Box and whisker plot.
Yeah, it's that.
Box and whisker plot. if that ever happens, you go up there where plot one is selected, just deselect it.
Got you. Okay. Thank you. Zoom in 6.
Yep. Zoom in 6. Perfect.
That one's white.
That's the same thing.
Do I need the grid or not?
I can't spell the other one. Well, what is it gonna cover at least like 10 of for, like vocabulary words in the section? Anybody else,
He'll
like,
probably
it's
just
just
look
what
at
the
it
word
and he'll be
means
like-
and then put it in your words.
He'll literally just probably look at it and be like, oh, that's a page.
Okay, so now we're going to click Y equals. And so to get absolute value bars, here we go. We're going to click math. We're going to go over to num. You see this? Num. And it says ABS for absolute value. Click enter. So now you see how I've got Y equals, and it already has the absolute value bars for me. So if I put in the absolute value of X and graph, everybody's function should look like this. Y equals the absolute value of X. Here's what the graph should look like. We just talked about let me go back. I forget, y'all guys can't see both. We just talked about here that for the absolute value of X, what are you showing? There it goes. We talked about for the absolute value of X, the domain and range. The domain was negative infinity to positive infinity. And the range was from 0 to infinity. We want to know, how does that compare if I had this function, g of x, which is 2 times the absolute value of x? Do you guys remember when we did stretches and compressions? Vertical shifts, left and right, up and down. So before we put this in our graphing calculator, what do you think the 2 is going to do to the absolute value of x? It does multiply. Is it going to change we're multiplying what? The x's or the y's?
The X. Because that's what's in the. Well. Yeah, the X. I think it's multiply the X.
Okay. So we think it's the x's?
Yes.
So let's put in our graphing calculator and we will find out. So we're going to go back to our y equals screen. Let's leave the absolute value of x the way it is. And now beneath it, we want to put in 2 times the absolute value of x. So I put in 2. Then I'm going to click math. Go over to absolute x. And now we're going to graph 2 times the absolute value of x in red.
You add those two in the bottom.
So now what got multiplied by 2?
The Y?
The y's.
Oh.
Right here, we used to have a point at 1, 1. But now the point is at 1, 2. We used to have a point at 2, 2. But now the point's at 2, 4. And see, all the y's are multiplied by 2. Remember, if it's on the outside of the function, it affects the x's. I'm sorry, I did it backwards. You messed me up. If it's on the outside of the function, it affects the y's. If it's on the inside of the function, it affects the x's. So if I go back and click y equals,
Oh, okay. I got you.
look what I'm talking about, inside or outside. When I think about inside the function, I'm talking about inside the absolute value bars. I'm talking about inside. Remember when we did vertex form? And we had stuff like x plus 3 squared? This is on the inside of the function. Or if it looked like this is on the outside. And I had a whole big spiel telling you guys the difference. Inside, outside.
So with that, with positive 2 making it more narrow, would that mean that negative makes it more water? Like
No,
it wouldn't?
no. So we'll review that again. If the number is bigger than 1, so like 2, 3, 4, 5, 6, those are vertical stretches
Oh,
that made
yeah.
it taller, more narrow.
Yeah.
If the number was 1, it looks just normal.
Or decimal.
If it's a decimal, if it's 0.5, 0.25, or a fraction, those are the compressions that make it shorter and wider. What does the negative do out front?
Does it just flip it? Right?
Negative is a reflection.
Oh, okay.
So we're looking in the other direction. So if I look at this, the question was about the domain and range of the red one. So looking at the red graph, what do we say its domain is? What x's could we plug in?
1, 2, 3, 4, 5, 6, 7.
So the domain would be
Just small
Negative
x's.
infinity.
negative infinity up to positive infinity. The domain didn't change. What about the range? Did the range change?
0 to. No, it didn't.
It's the same, right? So the domain and range is the same.
Oh, yeah, it is. Sorry.
So when we look at these two questions, let's just think about them. We don't even have to necessarily graph them. What if I had 1/2 times the absolute value of x? What would the domain be?
It'd be water.
It would be narrower, or sorry, it would be shorter
Yeah, it'd be.
and wider.
Yeah, because.
Right, this is when you cooch the graph.
Yeah.
That's what it looks like. Shorter, wider. Here, is this, what's its domain? Domain.
Negative infinity to positive infinity.
That's right. What's its range?
0 to negative infinity.
No. But you can never have 0 to negative infinity is one problem. Remember, you go from the lowest to the highest,
0 to positive.
but that's also correct. It would be 0 to positive infinity. If it was 0 to negative infinity, you have to say negative infinity to 0. Lowest to highest. The reason I'm such a stickler for that is because I've seen it missed over and over. Even teaching at Northeast, teaching college level kids, they do that. They put it backwards, and it's wrong. So I'm trying to get you out of the habit now. I don't know where y'all got that habit from, because I think I'm the first time you ever talk about domain and range,
Yes.
and you still hadn't fixed it. So I don't know where that comes from. What about this one? -2 absolute value of x.
It'd be flipped upside down.
Upside down and
It'd be narrow.
narrower. Its domain would be negative infinity to
Positive infinity.
infinity. Its range would be from,
Negative infinity to 0.
that's right, negative infinity to 0. Now, later on when we graph them by hand, you might rather it be a fraction, because that number is actually going to be the slope of our two lines. And when it's slope, it's easier as a fraction than a decimal. But right now with our calculator, it doesn't really matter. Now, let's look at this question. It says, Jay rides in a boat from his home to his friend's home in a neighboring state. The graph of the function, d of t, which is equal to 30 times t minus 1.5, shows the distance of the boat in miles from the state line at t hours. Assume the graph shows Jay's entire trip. Okay? Okay, so here it says, here's the graph. They give me the graph. It shows here the function is decreasing up until this point, and then it starts increasing. And his minimum distance from the state line is 0 miles. Distance from the state line. So the question is, how far did Jay travel to visit his friend? So remember, this is kind of a weird way to look at it. This is a function showing how far away he is from the state line. So what's happening here when the function is decreasing? What are we talking about Jay doing?
He's lowering the distance.
He's lowering the distance between him and the state line. So he's getting closer to that state, closer to the state line, closer to the state line.
And then he's getting further.
And then what happens right here?
He starts getting
He
further.
does this.
He hits the state line, and then what happens?
He's going
goes
further
away.
from his own state.
He's going farther from his own state, getting closer to his friend's house. He's still pulling away from the state line. That's what they're talking about happening here. So how far did he travel to visit his friend? Well, let's see. He started out 45 miles away from the state line,
That's 45.
and he ended up at 45 miles away from the state line.
Traveled 90 miles.
So he traveled 90 miles. He traveled 45 miles in his own state, 45 miles in the neighboring state, to give me 90 total miles traveled.
So where does this function come in?
They gave it to us.
What was
Is he
it?
talking about this part?
Yeah.
I don't know. The next question maybe asks us something with this.
Okay.
The other one, it gave us the graph. We just had to use the graph.
The rate it changes over time. Like whatever he does different.
Okay, but what is a rate of change? Like there's very specific things. When you hear rate of change, there's certain things I want to come to your mind.
From 2 hours to 2.5, how far to go?
Okay, but if they wanted to know that, they would say, how much distance did he travel? Right, that's not what they asked here.
So, I forgot what it's called, but you go up and over, tries overrun.
Okay, when you think rate of change, I want you to be thinking rise over run, the change in y over change in x, also could be called the slope.
Oh.
Right, we're finding the slope of the line. So in this case, his rate of change, what is the y value? It's his miles traveled over what is the x value?
The time.
The hours it takes him to do it. So what is my rate of change here? It's the miles per hour. What is miles per hour? It's speed. I don't know, how fast was the boat going? Have y'all following me at all, or have y'all completely checked out?
I'm following. I'm just.
So we're looking for what speed was the boat traveling between the second and the 2.5 hour. So how did we find the slope of the line? Colin said the rise over run. Right, so we could figure out how much did we rise to go from here to here. We go up. You guys tell how much that is?
3 over 2.
It's not 3. Because each one of these doesn't represent 1.
Up 20.
We didn't go up 20.
Went up to. We went up 15.
We went up 15. Right, because each bar represents 5. And then we went right
And
from 2 to 2.5.
about 30 minutes.
Half an hour. So we have traveled 15 miles in half an hour. So what's our speed if we're going 15 miles in half an hour?
About 20.
You guys don't know that? I mean, y'all, that's,
I'm
30.
30. 30 miles per hour.
if I go 15 miles in half an hour,
That's 30.
and I keep this rate going, when am I going to go the next half hour?
15,
And then how much did I go in the whole hour?
30.
No.
Right?
Colin's not Colin.
Where'd that dude go?
And again, we could get that by dividing. 15 divided by 0.5 is 30 miles per hour.